Hello everyone, my name is Fabian Brandt. I'm from the Chair of Multimedia Communication and Signal Processing of the Friedrich-Alexander-Universität Erlangen-Nürnberg. I'm very happy to be here today at the Picture Coding Symposium 2021, presenting my work, Switchable Motion Models for Non-Block-Based Interprediction in Learning-Based Video Coding. Before we start, I would like to have a quick recap about motion compensation video compression. As all of you know, motion compensation is a crucial part of video coding. It greatly reduces the redundancy in a video sequence. However, we need to transmit motion for that purpose. To transmit the motion information, we usually find a sparse representation of this motion field, which we can transmit before we reconstruct the dense motion field from this sparse representation. For example, this is implicitly done in block-based coding. Another possibility to obtain a sparse motion field is to use a sparse subsampling of the motion vectors and then interpolate the dense field from that. That is also what I will concentrate on in this work. A different approach here is also you can use a compressive autoencoder which transmits the latent space as a sparse representation. When we want to reconstruct a dense motion field from a sparse representation, we always need some model assumptions. These model assumptions greatly define the characteristics of the resulting dense motion field. For example, here on the right side we have a translational motion model and also an affine motion model. We can see that different content requires different motion models. The goal is now to adaptively switch between these models. For example, VVC is doing that by using block-based switching between translational and affine motion models with great success. However, right now there is no equivalent approach available for dense motion fields. This is a very interesting question because dense motion fields are typically used in learning-based video compression. In our novel approach, difference image-based motion model switching, the goal is to divide the motion field into segments as basing for the switching. We want to derive the segments in a way that we can repeat the same estimation at the decoder side also. Our approach is called difference image-based motion model switching, or DIMMS, and is, as the name already says, based on a difference image. I will explain this in a second now. We start by creating two different candidate motion fields by using two different motion models for reconstruction. Here we can see two examples. One is a motion field which is interpolated in a linear way with an affine motion model, and on the right hand side we have a translational motion model where all the vectors locally point to the same direction. From these we then generate two candidate images by performing motion compensation. Both of them could already serve as predictors, but we want to combine them in a smart way. From these two candidate images we first compute the difference image D. It is noteworthy that this difference image can be computed at the decoder side as well, because it only uses transmitted information. There are two central assumptions about the difference image D, which we use in our work. First, where D is large, we need a detailed partitioning. This is pretty straightforward because D gives the difference between the two candidate images. So when the difference is large, the switching can have a large impact, so you have to take special care about that. Whereas when D is small, both images are similar anyway, so we can tolerate small mistakes. Second, the ideal mask is locally correlated to the difference image. I will explain this on the next slide. Here we see the difference image versus the ideal mask. On the left hand side we see the sign of the difference image, on the right hand side the ideal mask. The ideal mask gives information for each pixel which of the candidate images is preferred here. Note that this is an oracle approach which we cannot use in practice. However, we can see that the sign of the difference images and the ideal mask share some shapes. You can see, for example, here and here there are similar shapes with a different sign. On the other hand, we can see similar shapes here and here with the same sign. So we can derive some shapes of the ideal mask from the different images, but not the sign itself. In the following, I'll show you how we can exploit that. First of all, we start by a pseudo-random sampling of the motion field. We sample in a way that the local sampling probability is proportional to the absolute value of the difference image. These sample points serve as seeds for the segmentation. Because we use these probabilities, we have more segment and therefore finer switching for larger values of D. So this fulfills our first assumption. We fulfill our second assumption by using a special kind of segmentation. We first split the image in a positive and negative area. So we can see this here. We have a positive and a negative area. We split the image and also the seeds, and then perform a nearest neighbor segmentation for the seeds in each part. Afterwards, we merge the segments according to the sign. So in the area which was negative, we have the segmentation from the negative part, and the part which was positive, we have the segmentation from the positive part. We can see that this preserves the edges of the sign image, and therefore also contains the shape information we have for the ideal mask. On the right hand side now we can see an example how such segmentation may look like. After you obtain the segmentation, we have to generate the switching decisions per segment. So therefore we just test both candidates for each segment and transmit per segment which of the models we chose. There are different criteria possible. For example, we could minimize the error energy or the overall rate distortion cost function. It is noteworthy here that the segmentation itself is for free in the sense of bitrate. Only the decisions cost rate. Let's now come to the experiments. In our experiments, we tested our procedure on the JVET test set. We estimated the motion using PyFlow and then performed the content-adaptive downsampling of the motion vector field for transmission. We then use two different interpolation methods. We use nearest neighbor interpolation, which corresponds to a translational motion model, and the linear interpolation, which corresponds to an affine motion model. We then perform a switching between these two models and compare ourselves against the block-based switching, which is a static approach, just dividing the image into a suitable number of blocks. Furthermore, we perform ablation studies for the sampling and segmentation strategy by testing our assumptions that we presented before. We evaluate on the prediction error energy in terms of PSNR and also the rate we need to transmit all necessary information. Let's start with a small visual comparison. On the left side we can see the result for linear interpolation, and on the middle we can see nearest neighbor interpolation. We can see that both of them have some errors. When we combine them by using DIMMS, our method, we can see that there are still some errors present which come from the linear or nearest neighbor interpolation, but the overall image has a higher PSNR, a lower error energy. For example, we can see here that there was a part taken from the nearest neighbor interpolation because the linear interpolation bends the image here too much. On the other side, we can see here that the nearest neighbor interpolation produces some artifacts. You can see we used a more smoother approach from the linear interpolation. Let's look at this objectively now. In this diagram, we show the switching gain for different rate of switching information. When we use more rate for switching information, that means we segment our image into finer segments, which leads to an increased rate, but also to an increased quality. This purple star here shows the result when we do not use switching, but instead use the additional bit rate to transmit the motion vector field at a higher quality. We can clearly see that transmitting structured site information for switching beats this approach. We can see that our method, DIMMS, beats the block-based switching for all bit rates. Furthermore, when we use just 0.002 bits per pixel for switching information, which in this example is about 10% of the motion bitrate, we can already gain about 0.7 dB here, which is about half the way to the oracle segmentation. The oracle line here just denotes the case when we always pick the best candidate image per pixel, which is not a practical approach at all. For the rest of our evaluation, we will stick to this 10% of the motion bitrate for switching. In this diagram, we now show the combined rate for motion vector transmission and switching information compared to the prediction Pearson-R. We can see again that our method, DIMMS, performs best of all cases. We can see there is no surprise that the nearest neighbor interpolation performs worst, and linear interpolation performs second. You can also see that since our method just combines linear nearest neighbor interpolation in a smart way, that this system actually works because we can achieve a better result than either of them. Furthermore, we see that DIMMS clearly beats block-based switching for all rate points. When we look at the results in terms of average gains over all bit rates, we can see that DIMMS beats the baseline by 0.40 dB. In comparison with block-based switching, we only achieve 0.11 dB gain. We then performed 2 ablation studies to show the validity of our assumptions we showed at the beginning. In the first one, the sampling ablation study, we performed a uniform sampling over the motion field and then proceeded as before. This way we were only able to gain about 0.18 dB. So that shows that our approach of sampling more dense where the difference image is large is actually valid. The second one, the ablation study for the segments, we performed the sampling according to the probabilities, but we did not interpolate with our special edge preserving method, but rather used a simple nearest neighbor segmentation. With this method, we were only able to gain about 0.27 dB. Both of them are much smaller than our overall gain of 0.40 dB for DIMMS, which clearly shows that our assumptions we started with are valid. In conclusion, we can see that the switching between different motion models is definitely also beneficial for dense motion fields. This was already shown, for example, in VVC with the introduction of affine motion, and now we can see that this also works for dense motion fields. We can also see that our signal adaptive approach is superior to any static approach we tested, and that by using our assumptions about the difference images, we were able to also get some additional gains. As an outlook, we plan to integrate the system in a full video coding pipeline to show that it also works when we use it in a whole coding system with residual coding. Thank you very much for your attention. I'm looking forward to your questions and a nice discussion.